Thank you, everyone. Good afternoon. Again, my name is Bill Walrond. I'm with Caserta. Just 30 seconds about Caserta. What we are, we're a data analytics consulting company, and we specialize in data solution implementations in the cloud. That's pretty much all we do. We've been in business since 2001. And we focus on data lake architectures, data warehousing, ETL orchestration, advanced implementations, but also strategic consulting as well. My position is that of a principal consultant, so I lead teams of data scientists, data analysts, and other analysts in our implementation projects among our clients in all kinds of industries and all kinds of sectors. So let's get started. Real brief history. Along came big data and distributed processing for the masses and predictive analytics for the masses. A lot of revolutionary change over the last 5 to 10 years. It's been fantastic. It's changed my career, my life, and I think a lot of yours. Along with that, it's brought different data structures. We've had the rise of big data has led to flat data structures, generally better for data science and driven by the needs of machine learning and data science. This has been very good, but meanwhile, there are challenges elsewhere. There's still companies, believe it or not, enterprise companies still having challenges answering basic fundamental questions. How many customers do I have? What was my revenue last quarter? How many promotions are expiring next month? These are fundamental questions that the volume of data has, while the volume of data has grown over the last few years, the capability of answering some of these basic questions, is still as challenging now as it ever was. So we kind of recognize a potential where BI tools that have traditionally been the area where these sorts of operational questions have been answered, can maybe use the same data structures as data science and use them efficiently. So is that possible? And the answer, a little foreshadowing, is yes, but with some thoughtful data architecture. So that's our objective here. So we're going to explore data architectures that make sense for both data scientists and business intelligence analysts. So there's no need to replicate data to serve two functions. One repository can serve both. But before we get there, I've been challenged by clients that say, well, look, this is big data, it's cloud technology, cloud storage is cheap and abundant. Who cares? You can give data scientists everything that they need. You can give business analysts everything that they need, and let everybody do what they need to do. So what's the problem with that? Well, the problem is consistency. When different groups have access to the same data but are doing the same raw data but are doing different things, we run into some problems. So imagine a situation where we have a business intelligence data lake and also a predictive analytics data lake, essentially drawing from the same source data, but they're maybe using their own rules to calculate certain metrics, like customers. My data scientist says, well, I've got 1.027 million customers. My business analyst says I have 1.078 million customers. So, what happened to those 6,000 customers? Well, if you're a data scientist, you might sort of write that off saying, well, that's not, 6,000 customers, that's, significant, statistically insignificant. But if you're a finance manager, you need an explanation for what happened to those 6,000 customers. And once that conversation starts, now you're headed down a pathway of backwards data reconciliation, which is just a nightmare of an effort to do. If you've had to been a part of that, that's a colossal waste of time and frustrating in the end. So we want to avoid this. So how do we do it? We aim to create a single source of the truth. So a single repository where we know certain constants are validated and everyone agrees that this data is correct and it'll produce verifiable results. Okay, so how do we do this? So we're going to aim to create one data lake framework to serve both business analytics and data scientists. So how do we go about this? So we start by looking at and considering the requirements of both areas. Both business analytics and data scientists need to do certain things right from the get-go. They need to, I think the very fundamental aspect of ingesting data directly from sources reliably and flexibly is just a fundamental action that needs to occur for either business analysts or data scientists. I've never met a data scientist who said, no, I want to take care of all the ingestion and I want to take care of that all myself. That's just not happened. So this is a great area to start. So what do we do? So we start by creating a common framework for landing data. This is receiving or requesting raw source data. And we need to support a key set of features and capabilities. We need to land data that's either batch or streaming. We need to either accept it being pushed to us, or we need to pull it from our sources. We need to support a variety of endpoints, cloud storage, SFTP, APIs, anything that really presents itself to us. And we pull that data into a landing area, which is going to be temporary for our next step. Ingestion. So first things first, we're going to ingest this raw source data. So what does that mean? Well, I'll get into the details in a second, but essentially it means that we're going to take this data, start reading it, start cleansing it, and then we have to persist it, and then repeat this for every file, for every source, for every stream of data that we have. Okay, so cleanse, the dirty details. What does cleanse really mean? Well, it means a list of things. So first of all, we need to handle a variety of file formats. Well, basically any file format that comes to us. We need the capability of handling JSON, CSV, fixed width, ASCII, EBCDIC, comp3. Anybody hear of comp3 before? Yeah, me neither. But we have to, any file format that comes to us, we need to handle. In that raw data, we have to remove the bad stuff. And raw data has bad stuff that causes problems later. Header lines, blank lines, non-printable characters. I could share a time I was debugging a query with a colleague, and the query was just, wasn't that it was producing bad results, it just wouldn't work. It was erroring out. No idea what was going on. Data was showing, didn't look like it had any problem. after days of tracing this data back, we finally figured out that there were 0-byte characters in some of the columns, in a very few number of the columns, but those were columns that happened to be part of the operation of this query. The function was trying to operate on those columns, and it was just blowing up the query. So get rid of that stuff in the very beginning. Apply a schema. This means check the source data that it matches the number of expected columns that source data is supposed to have, and that each column matches its expected data type. And check that. And as you check it, you're going to run into problems, which means we're going to need robust error reporting as part of this. So this means that we're going to be collecting rejected rows and making sure that we record specific errors by column over the entire set, not just the first error that you hit. So it turns out that this is more work than you think. It's not rocket science, but it's more work than you think. But again, all things that any data scientist or business analyst is going to need before they even start asking any questions about the data. Okay, so then, now we have some clean data. What do we do with it? We persist it. But here's the key aspect at this point. We still want to save this same data, this ingested, cleansed data, with the same schema as that it came to us in. That's a very important point. I'll come back to that a little bit later. And as we persist it, we want to make sure that we use a suitable storage format. We really like and have a lot of success with Parquet. It's self-describing schema, advanced schema support, advanced data types. It's columnar, it's typed, so integers are integers, dates are dates, and so forth. It supports partitioning and compression and encoding, so this is a good choice. But there are others as well. We also want to make sure that we establish a logical bucket namespace. And this needs to be organized and easy to understand. I'll give an example later, or just a second. After we persist this data, we want to archive the raw, unmodified, and uncleansed source data. So we want both around. We may, for our archive data, we may use a different ILM kind of policy for that data, but we want that data around in case of situations where we need to reload. So that's a good practice to keep the archive around in its unmodified, uncleansed form. So you guys may be using your own namespaces in whatever way makes sense for you. Here's one example that we used on a recent project. Again, just parcel the namespace out in a way that makes sense, company, division, project, but include an element of your DevOps life cycle for dev, stage, or prod. That's important. An ingest lake, reject, archive folders, and so forth. You want a good namespace like this so that you can have an opportunity to do other types of scripting that you may need in the future for whatever needs come up at the time. Okay, so at this point we've ingested the data, we've cleansed it, we've persisted it. So far, everything that we've done is useful and valuable for both business intelligence and data scientists. Okay, now what? Okay, so now we can start to conceptualize our all-purpose data lake. So what this entails is we're conceptualizing a specialized set of data structures. Clearly, source data isn't really created to exactly answer the specific questions that we might have, right? The way that we approach the all-purpose data lake is instead of coming at it from the source data perspective, we sort of approach the problem from what are the range and the body of questions we think that we're going to need to ask of this data, and what are data structures that could look like that would be suitable for answering those questions. Okay, so how might this be different than any other data lake? Well, when I ask people, like, what do you think a data lake is, the most common response I get is, well, it's raw data or unstructured data. Okay, I understand that, but I think we have an opportunity here, especially given the capacity that we have with our cloud architectures, with the capacity to perform machine learning over this abundance of data. We also have the capacity and the concepts to create structures that that serve more than one use. Okay, so more themes on the model data structures. So we want to create data structures that are organized to reflect more so the fundamental aspects of our business or customer activity, whatever it is that we're seeking to ask questions about. This really represents the intersection between the source data and the people that are trying to understand it. With the idea, the theme of making data analysis as easy and straightforward as possible. We want to focus on how to answer the question and the information that the data is actually telling us, rather than details about data types and cleansing erroneous characters out of data. We want to make sure that this data is organized in a way that we can ask and answer our questions easily. Okay, so here's where the old meets new theme sort of comes into play. If you're from the data warehousing world, the star schema won't be anything new for you. Raise your hands. Who's familiar with the star schema concepts? Pretty mix of people. Okay. The star schema is meant to answer questions like this. So it's the star schema is sort of divided into two kinds of tables: dimensions and facts. Dimensions are for things like customers or products, promotions, parts. Sometimes it's thought of as reference data, if you will. Whereas facts are tables that store events, that store page views or clicks or orders or cases or sales. Facts can also be like a snapshot in time, like a snapshot of a state of something at a particular moment in time, and captured on a certain interval. Now, this kind of scheme has several advantages. Number one, the star schema approach works well with a lot of business reporting tools. They're already set up to handle this, like Looker, Click, Tableau, many, many more. There's a lot of great options out in the marketplace. In most cases, these tools anticipate data structures like this, and their whole setup, if you present data structures to these tools in this way, they're specifically meant to help you construct your analyses if the data is organized this way. Sort of a side note here, a side benefit here is that In a lot of these tools, you can set up drop-down filter boxes and so forth, and so the population of those drop-down filter boxes is a lot faster when they're working off of dimension-type tables. Now, I've seen other colleagues try and populate such tables or such things by doing a select distinct over billions of rows, trying to come up with a distinct list of locations to populate a drop-down filter box with, and it doesn't go over very well. But the key advantage of dimensions is about handling change. It turns out things change in the world. And customers change their names and emails, addresses, and so forth. In fact, most things are likely to experience some kind of change over time. This is really where the convenience and the power, the benefits of a dimensional kind of model come into play. Because the dimensional structures offer an organized method for handling changes. There are a number of options. You can fully replace the dimension if you want. Oh, I got a new customer file. Let's just replace the old one. You can treat changes as versions. You can get this is called a type 2 dimension, whereas we detect changes in dimension data, instead of replacing it, we actually store a new version of that row marked with a beginning and an end time for when that row's version was current for. Or you can come up with any number of unique ways of handling changes within dimensions for any particular situation. We've come into different clients that have different requirements. There's no hard and fast rule written in stone about exactly how to treat a change of a dimension. You treat it the way that you need to. But the great part about it is you get to make that choice just for that piece of data. And just, from a Spark perspective, Spark is an excellent platform for processing dimensional loads. This statement right here has been invaluable just for finding differences. The subtract method is your friend if you're doing a lot of Spark programming. But the fact is, without dimensional structures, handling changes could mean massive replication of large data sets. So imagine if you need to update all the customer attributes in a massively flat, multi-billion row table, so really, the only approach that you have is just taking that table, replicating it, and joining in all of your new updated data and writing the whole thing back out again. So that's sort of a drag, right? Versus just processing the changes in that particular dimension. Next, we persist the facts and dimensions in the cloud storage, similar to how we ingested the data, again under a logical namespace. But one other thing, we also want to replicate the same data sets in a large-scale SQL database service. I'll talk more about that in a minute. So this is good ones out there: Redshift, BigQuery, Snowflake. There's many others. They're all very capable. And so when you put all this together, it sort of looks like this. We talked about the cleansing action, a cleansing activity in the data lake, in the ingest lake rather, that's persisted in the ingest lake. Source data in the ingest lake then can be transformed into our modeled structures in our modeled lake. This data in the modeled lake then becomes our truth. So, and metrics calculated based off the model lake are governed, they're curated, they're all agreed that those metrics calculated off of the model structures in the model lake are the, quote, official numbers or the truth. Okay, then we take that data and we replicate it into a SQL service of your choice. So that same truth is available in your lake and your SQL service. So in this way, BI analysts who typically will function off of your SQL service and through their tools can query and have access to that same truth through the SQL service. But at the same time, data scientists can have access to that modeled lake data, that truth data, through their own data science workspace. Data scientists don't really care where they get the data and get it from the SQL service as well. It's just as fine. But the point for them is that their sourcing of their data for their predictive modeling activities comes from the same exact source. And there's really nothing preventing the data science folks from also querying the ingest lake as well. But they need to do so at their own risk because they may be analyzing elements or source data that might not exist yet in the modeled lake. And they might be encountering data that others in the organization haven't used yet and may just need to do more rigorous analysis on that data. Oftentimes what happens is if data scientists need to go back to the ingest lake, they'll produce an analysis and say, hey guys, there's data in the ingest lake that's valuable that we didn't model and include in the modeled lake. So let's work on an enhancement to the model lake and add that data in. That frequently happens. Okay, so at the beginning, I talked about flat data structures. So let's get back to this topic. So in this idea, will data scientists be able to assemble the flattened structures, which are best for predictive analytics? Well, yes. The star schema structure is optimized to enable joins to execute efficiently. On flatter, unmodeled structures, joins could be a problem. There's nulls, there's other conditions that may cause problems. But star schema joins are generally executed efficiently. So data scientists are welcome to join together every table, every fact and dimension they need, and include all the attributes they need for their work. To conclude, business intelligence and data scientists' interests can be served by the same underlying data lake, but it takes agreement, some planning, some modeling, and a thoughtful data architecture. And then, our experience is that Spark is an excellent platform to make the all-purpose data lake a production reality, and it's been a fantastic experience to use Spark to do that. Okay, so questions, 44 seconds.
Any questions? Yeah. Just got time for a couple.
Hi. So with your data lake at the end, are you going to, do we incorporate, or would you say it would be a good idea to incorporate various aggregations of the data downwards so that it's not only the truth, but also the aggregates of the truth?
Yeah. So the question is, are aggregations valuable? They can be valuable. I think you have to use your best judgment about what you're aggregating and then how that's being used. and then how frequently those aggregations need to be updated. So that becomes a factor. So for example, if the constituents need more, if the frequency of updates are such that that aggregation needs to be updated very frequently, maybe there's a different strategy to consider. But frequently that's a good strategy.
So on the last part, you had replication over here.
Yes.
You had the replication where you were replicating from data lake to SQL.
Yes.
Now, what would be, if you can, on that last part, what would be your recommendation on how much of the replication to be done? Is it like every single table to be replicated, or part of it? And how do you say we have like huge table, big size table?
It's a good question. Yeah, it's an excellent question. So my recommendation is replicate 100%. So the same data, the same truth that you have in the modeled lake, you want available to both constituents, all of it, right? So you want all of that truth available from the SQL service and the BI analysts, and you want all of that truth to be available to the data scientists. Every situation is going to be different. There could be constraints involved, but that would be my going in, strategy.
Thank you. My question is also regarding this replication database. I cannot fully understand the rationale behind having it. Like, that's my question. What's the rationale behind having to have this replication database? Because I know currently BI tools could connect to the data lake seamlessly.
Okay, great. So why replicate to a SQL service instead of just making the the modeled lake available through the BI tools to through like a JDBC connection through Spark or whatnot? So that's the right question, right? Yeah. So our experience here is that these SQL services are in some cases very, very efficient onto themselves, and that the tools work better. Some of these tools are very focused on the kind of SQL service it is, and generally prefer to connect to a SQL service like BigQuery is a great example, Redshift. It is possible, but it also incurs, you have to make sure that that there is a appropriately sized cluster available to service those queries pretty much whenever it's needed. In contrast, the SQL service is usually up and available, all the time, and that's sort of rolled into the cost structure of that service. So that's been our experience. I hope that covers the question.
All right, let's give them one more round of applause, and then we'll